Okay, so now let's start thinking about relative dating. So remember, this is about putting a sequence of rocks into a chronological order, but there aren't any numerical ages associated with those rocks. So what are the techniques that we're going to use to actually come up with that relative date? So if you don't have access to radiometric dating methods to give you that number, you have to relatively date your sequence of rocks. So the method will not produce a definitive date. All it will tell you is that rock A is younger than rock B, and that rock B is older than... sorry, let's try again. Screwed up there, didn't I? It will tell you that rock A is younger than rock B, and that rock C is older than rocks A and B, for instance. Something along those lines. So what you end up doing is you end up producing a sequential order on your observations. You come up with a chronological history of that rock sequence based on what you observe. So this method allows geologists to interpret geological history and develop the relative timescale, which is, to you and me, the geologic timescale. So there are 7 principles used in relative dating: superposition, original horizontality, lateral continuity, cross-cutting relationships, inclusions, baked contacts and zones, and fossil succession. Fossil succession is also sometimes called faunal succession. Now we're going to deal with 7 in the next lecture, so we're only going to focus on 1 to 6 right now. So the idea of relative dating can be traced back to Nicolas Sterno, and Steno was a Neptunist. So what he was doing is he was making observations related to how rivers flood. So when he looked at the river and how it's flooding and what happened afterwards, he noticed that the flood waters would deposit a layer of sediment over the area. Now what he did is he then extrapolated this process and took it to a global scale, and he put it into the context of the Great Flood. So he was using a biblical standpoint. Now the observations he made, though, if you just ignore the biblical context in which he put them, his observations are actually accurate, and his interpretation of them is also accurate. So his work is defendable, with the exception of the context into which he placed the data he collected. So what he noticed is that every time a river floods, it deposits a layer of sediment. The next time the flood occurs, a new layer of sediment will be deposited over the top. Then the next flood, another layer. Next flood, another layer. And so what he realized was that every time a river floods, it will superimpose a new layer of sediment over the layer of sediment deposited by the previous flood. And he also realized that once lithified, these layers of sediment would become rock. So this means that if you look at a sequence of rocks, it would mean the youngest sediments would be at the top of that sequence, and the oldest sediments would be at the bottom. And that's the principle of superposition. If you have a sequence of rocks, the oldest rock will be at the bottom, and the youngest rock will be at the top. And that works for about 90–95% of cases. There are instances when your sequence of rocks can be overturned, in which case the oldest rock would be at the top and the youngest rock would be at the bottom, but that's a relatively uncommon occurrence. So he also noticed that sedimentary particles settle out from floodwaters under gravity, and so this will produce nice horizontal layers of sediment. And so this is the principle of original horizontality. So original horizontality states that because the sediment is deposited as a horizontal layer, when that layer of sediment gets lithified, it will also produce a horizontal layer of rock. Because remember, if you have a layer of sediment and you try and tilt it, well, that layer of sediment is going to slide, isn't it? It won't stay as a nice horizontal layer. So that means in order to have a nice horizontal layer of rock, your sediment needs to have been deposited as a horizontal sheet, then turned into a rock, so lithified, and then if it's been tilted, any tilting has to occur after the lithification. So if we look at this picture here, we can see straight away we have a beautiful example of an angular unconformity. There's our unconformity running along here. We can see the rocks below the unconformity are dipping, and the rocks above the unconformity are horizontal. But this also tells us that these rocks here must have been deposited as horizontal layers of sediment, lithified as horizontal sheets, and then deformed. That therefore means that these layers of rock here must be older than these layers of rock up here, because these layers of rock are nice and horizontal and they haven't been deformed. Okay, so this allows us also to begin to gauge which layers of rock are older relative to other layers of rock. The final observation that the Steno made was to do with the continuation of the layers of sediment which are deposited. So when he tracked the layers of sediment deposited by floods, as you move laterally, you'll steadily see that your layer of sediment will get thinner and thinner and thinner and thinner, and then eventually disappear. It will, in geology, it will do what we call pinch out. So that's option number one. The further you get from the source of the sediment, the thinner the layer of sediment will become, and then eventually it will pinch out and disappear. The other possibility is that your flood, in layer of sediment deposited by your flood, you'll be able to track the layer, track the layer, track the layer, and then you'll come up against some kind of vertical surface, like let's say a cliff face. Well, obviously your layer of sediment will have to terminate against that cliff face. So essentially, this is the principle of lateral continuity. And the principle of lateral continuity states that a layer of sediment will continue in all directions until it either thins and pinches out or terminates against the basin margin, which is some kind of vertical surface. So if we look at this picture here, this is a seismic section, okay? So, this is an image produced by geophysicists, and it's showing you the layers of rock in the subsurface. So what we can see here is we have a stack of sedimentary rocks in this basin here. Okay, so there's the basin there. So if you follow these layers of sediment, you'll see when they get to the basin margin, done. They terminate right there. So that's your layer of sediment terminating up against a vertical face, which will be your basin margin. In this diagram, your layer of sediment is continuing. It's getting thinner and thinner and thinner the further it gets from the sediment source, and eventually it pinches out and disappears. So what Steno is essentially saying is that no layer of sediment will continue forever. It will eventually thin out and be lost and be replaced by a different layer of sediment. So following Steno's work, we now have an observation by James Hutton. So as I discussed, he noticed that rocks like granite represented magma which had intruded a pre-existing sequence of rocks. And so this led Hutton to come to the principle of cross-cutting relationships. So he realized pretty quickly that any igneous body, like this dike here, or any fault that cuts a pre-existing sequence of rocks must therefore be younger than the rocks which are cut. So in order for this dike to have intruded this sequence of rocks, well, clearly these rocks must have been there beforehand, and then the dike must have been intruded. Same with this fault here. These rocks must have been there beforehand, and then they were cut by this fault. It doesn't make sense any other way. So the principle of cross-cutting relationships simply states that dikes and faults must be younger than the rocks which they cut. So next we have the principle of inclusions. So the principle of inclusions is extremely straightforward. It's very useful, particularly when you're trying to determine the relationship between igneous bodies and the host rock, especially if that host rock is a sediment of some kind. So the principle simply states that if you have clasts, so fragments, of rock A contained in rock B, then rock A must be older. So if we look at these two examples here, we can see two different situations. So in example A, we have a granite down here in pink, we've got a sandstone in yellow, a mudstone in brown, and the limestone in this kind of creamy grey colour. So what we can see here is that the sandstone, the yellow layer, contains pieces of the granite, the pink layer. So we can see the clasts, the fragments of granite there, contained within the sandstone. Well, in order for those pieces of granite to be in the sandstone, clearly the granite must have been there first. It must have been weathered to create the fragments, and then they became incorporated into the sandstone. Therefore, the granite is older than the sandstone. Now we have a different situation. In this instance, we have a granite which contains pieces of the sandstone. Well, in this instance, what's happened is the granite intruded the sandstone as magma, and pieces of the sandstone fell into the magma. They didn't melt, they just floated around in the magma, and then eventually when the granite solidified, you ended up with these pieces of sandstone sitting within the granite. So in this instance, we have sandstone in the granite, therefore the sandstone is the older rock, and the granite is the younger rock. So that's the principle of inclusion. It's a very straightforward principle. So when you are looking at the diagrams as part of the assignment associated with this particular lecture, always take some time and just take a second and have a look at any class that might be in the block diagrams that you're given, because that's going to give you a good hint about which layer of rock came first. The final one we're going to look at is the principle of baked contacts or baked zones. So this one is related to the heat put out by some kind of magma intruding a sequence of rocks. So obviously when your magma intrudes a sequence of rocks, be it as an intrusion or a dike or a sill, well, that body of magma is going to heat up the surrounding rock, and it's going to end up contact metamorphosing that rock. So the effect of the contact metamorphism associated with the intrusion is called essentially will produce a zone called a baked contact. So if I just skip to the next slide, here we have a sequence of limestones, and you can see we have a sill coming through straight here. Okay. Well, if you look to the top and the bottom of the sill, you'll notice that the rocks here are a lighter colour than the rocks up here. That's because the heat from the magma, which formed the sill, essentially has cooked the rock above and the rock below. So it's contact metamorphosed it. This zone of contact metamorphism associated or caused by the heat is also referred to as a baked zone. And it quite clearly tells us that this limestone must have been here first, because as the magma was intruded to form the sill, it cooked the rock below it and it cooked the rock above it. Therefore we know the rocks below and above must have been there before the sill was in place. Okay. So actually, do you know what? I'm just going to skip back to the next slide. Now over here we have a lava flow. So here's our lava flow in the grey, and here's the sandstone that the lava flow moved over, which is this kind of yellow grey coloured rock. Now you'll notice at the bottom of the lava flow it looks really, really rubbly, and that's because it contains pieces of the sandstone. So straight away, if we go back to our principle of inclusions, we have our lava flow containing pieces of our sandstone, therefore that means the sandstone must have been there beforehand. You'll also notice that the heat from the lava flow here has actually gone and baked the top of the sandstone layer and turned it red. Once again, this is another indicator that the sandstone layer was present before the lava flow was deposited over the top. Okay, so both of those pieces of information, the inclusions and the baking, tell us the sandstone was there first, then the lava flow went over the top of it. Now the thing is that if you were to look at the top of this lava flow, any rock above it would not be baked, because there was no rock above the lava flow when it was extruded onto the surface of the Earth. So if we look at our it's a very simple diagram here, this is our lava flow coming over the surface of the Earth. It's going to bake the rock below it, but because there's no rock above it, that means there's going to be no baked zone. So if later on sediment gets deposited over the top, the sediment on top of this lava flow will not show a baked zone. And that's an indicator that what we're looking at is a lava flow rather than a sill. So let's look at the situation here. Here's our sequence of rocks. Okay, so when we have a sequence of rocks like this and we have a horizontal igneous sheet in it, like a sill or which could be a sill or a lava flow, one of the questions we have to ask ourselves is well, what is it? Is it a sill or is it a lava flow? So let's think of the lava flow situation. So in the lava flow situation, what we're going to see is, layer of rock number 1 would have been deposited, then layer of rock number 2, and then the lava flow came over the top. Now obviously the heat from the lava flow would cook the top of layer of rock number 2. Pieces of rock number 2 would also become incorporated into the lava flow. Then the lava flow solidifies, and then layer of rock number 4 is deposited over the top. Well, layer of rock number 4 wasn't present when the lava flow was extruded, and so it wasn't heated by the lava flow. So layer of rock number 4 will not have a baked contact. Layer of rock number 4 will also probably include pieces of, the lava flow. Let's say maybe a basalt or something. And so we'll see pieces of our lava flow within layer of rock number 4. So this clearly tells us that layer of rock number 1 was deposited, then 2, then 3, then 4, 5, and 6. So that would be an example of a lava flow. Now, what happens if we have a sill being placed instead? Well, as you can see, what we end up with looks very similar, doesn't it? We've got 1, 2, there's layer 3, 4, 5, 6. In this case, they've even thrown up an additional layer, which they called 7. So how do we know that this is a sill? Well, remember, a sill is a horizontal sheet of magma injected between layers of rock. So here we go. So we have layer 1, layer 2. Now notice layer 2 has a baked contact, so clearly layer 2 must have been present before the sill was in place. And then we have layer 4. Layer 4 also shows a baked contact, so layer 4 must also have been present before the sill was in place. If we look carefully, we will also find pieces of rocks 2 and 4 within the sill. So both the principle of inclusions and the baked contacts will tell us that the sill must have been in place after layers 2 and 4 had been deposited. So layers 2 and 4 form, and then the sill gets injected between them. So this is how we tell the difference between a sill and a lava flow when we see a sequence of rocks like this. We use the baked contacts and we use the inclusions. So now we need to have a think about how fossils are useful in terms of relative time. So the usefulness of fossils as a means to match strata of similar ages was first noted by William Strata Smith. I should point out that there were actually earlier examples of this, so Leonardo da Vinci actually made a similar comment, but in terms of actually applying it to rocks on a large scale, William Strata Smith was arguably the first person to actually do so. So, as he travelled around the United Kingdom, surveying, doing surveying work for canal building, mining, quarrying companies, he took notes of the rocks and the fossils that he saw as he was going around. So what Smith hypothesized was that if the oldest rocks are at the bottom of the sequence and the youngest rocks are at the top of the sequence, so that's the principle of superposition, the same must therefore apply to fossils. So if you have a sequence of fossils, the ones down at the bottom of that sequence will be the oldest and the ones at the top will be the youngest. He noticed that the sequence of fossils, especially groups of fossils that he saw, which were present at one locality, is consistent from area to area. So as he was going around, he would see the same groups of fossils occurring in rocks, and what he realized was that he could use these groups of fossils to actually correlate between those rock layers at different locations. He could use them as a way of saying, right, these rocks were clearly forming at the same time, even if they were, tens or hundreds of kilometers away. So what he had done is he'd therefore found a way to relatively date sedimentary rocks from different areas, just using the fossil assemblage. And his methods are still being used today by sedimentary geologists, so his technique still holds good. So his knowledge allowed him to accurately predict the fossil assemblage that would appear in rocks at a locality that he had not previously visited. So if he had some idea of what rocks, what the age of the rocks would be when he was going to a location, he could actually predict ahead of time what fossils he would be able to find. And this is very, very important because by doing so, he was testing his idea. And because he got a positive result, he was backing up his idea and proving that his theory worked. So independently of Smith, Alexandre Bouguereau was making similar observations of the fossil succession around Paris. So his conclusions were the same, but his data set was a little bit more limited because he really stuck in the area around Paris, didn't really strike out into the whole of France to look for examples. So yes, same work, slightly different, slightly smaller data set. So the basic principle is that if we're starting off at location A and we see fossil X, Y, and Z in our rock, so then we go to location B, we see fossil X, Y, and Q. So the first question is are these rocks going to be the same age? Well, yes, fossil X is present, yes, fossil Y is present, but fossil Q is present at location B, so fossil Z is missing, and fossil Q isn't present at location A. So although they share two fossils, so they're probably of a similar age, they're not going to be of the same age. So what about location C? Well, at location C, we have fossil X and fossil Y. would that make location C the same as location A in terms of its age? The answer would also be no. Because yes, once again, we do have fossil X and we have fossil Y, but we're missing fossil Z. So just like location B, because you have X and Y, chances are location C is of a similar age to location A. So they're probably relatively close in age, but without fossil Z to definitively allow you to tie them together, you can't say they were forming at exactly the same time. What about location D? Well, at location D, we have fossil X, fossil Y, and fossil Z, just like we do at location A. So we can use that to say, right, these rocks were forming at the same time. They are contemporaneous with one another. So this is the very simple technique that William Strata Smith came up with, and it's, as you can see, it's very simple and it's highly applicable to geology even now. So obviously this then brings us on to the seventh of the methods of relative dating. So if you remember, we have superposition. That's that's the oldest rocks will be at the bottom of the sequence, youngest rocks at the top. Original horizontality. All layers of sediment are initially deposited as horizontal sheets, and therefore any tilting must have occurred after lithification. Lateral continuity, a layer of sedimentary rock will continue until it either thins and pinches out or hits some kind of vertical basin margin. Cross-cutting relationships, faults and dikes must be younger than the rocks which they cross-cut. Principle of inclusions, any inclusion within a rock must be older than the rock within which the inclusions occur. Baked contacts or contact zones, essentially any baked contact must be younger than the rock that is being affected, and therefore also what is doing the baking must also be younger than the rocks which are being affected. And then finally we have fossil succession, which is also sometimes called faunal succession. And this principle is relatively straightforward. It just states that fossil assemblages, so groups of fossils, succeed one another through time in a regular and determinable order. Very straightforward. All it's simply saying is if we find a fossil as a geologist, we can work out where it sits in the sequence, because we know that the fossils occur in a set order. Geologists have spent hundreds of years now trying to get the fossils into the correct order, knowing when a fossil first appears and then disappears, so we know where they sit in time. And so as a geologist, as soon as you find a fossil and you can identify it, you know exactly where that fossil sits in geologic time, because the order is regular and determinable. So it's relatively straightforward. So all that's saying is if you find a fossil, you can work out when in geologic time it formed. So for every fossil, geologists get two data points. The first data point we get for a fossil is its time of first appearance, so when it first appears in the geologic record. And obviously we also get its time of last appearance, the last time it's seen in the geologic record. The majority of common organisms, especially shelly marine creatures, have very long histories, so they're actually relatively difficult to use for dating. So, there are some organisms, especially one of them in particular is called Lingula. It's a type of shellfish. It lives in sandy sediments and in beach and shallow water environments. That's been around for about the last 480 million years. So in terms of trying to date a rock, that's pretty bad, because you won't be able to know whether your rock formed 480 million years ago or last Tuesday. So there are some fossils which aren't good for dating rocks, but there are some fossils which are extremely helpful. And typically the shorter the period of time during which a fossil existed, the better it is for dating rocks and correlating between rocks. So using a fossil assemblage, which means using more than one fossil, makes our lives a little bit easier. So we can use several different fossils as a reference point simultaneously. So this means that if we have an assemblage of fossils A, B and C, well, there's only a very limited portion of geologic time during which fossils A, B and C could possibly have coexisted together. So in this instance, what we can do is we can take fossils, even if they have these very, very long timescales during which they were present, we can still use those timescales and look for the point where they overlap, and that's also helpful to us. So sometimes we don't just rely on one fossil, we'll actually use multiple fossils to help date and correlate our rocks. So when we are talking about sequences of rocks and the erosion, of those sequences of rocks, well, you have to ask yourself, well, hold on a minute, how can you prove that rocks have been eroded to, create sediments? Well, the first situation is we can see it, can't we? We know that rocks are constantly being broken down, mountains are constantly eroded, producing new sediments that get transported by rivers, etc., etc. But if we look in the rock record, we can also see indications of erosion having occurred. And this comes in the form of unconformities. So an unconformity is a surface, which is part of a sequence of rocks, that represents a portion of lost rock. So it means from a geologic point of view, as we've lost rock, we've lost time. So unconformities come in four varieties. The three most common varieties are a disconformity, an angular unconformity, and a nonconformity. So in the case of a disconformity, we have horizontally bedded rocks below, horizontally bedded rocks above, and the unconformity itself is undulating. It's horizontal, but it undulates. In the case of an angular unconformity, we have dipping rocks below the unconformity, we have horizontal rocks above the unconformity, and the unconformity itself is the contact between these tilted rocks and the horizontal rocks above. And then finally we have a nonconformity. So a nonconformity occurs between an igneous or metamorphic rock and sedimentary rock. So here's our sedimentary rocks there. Here's our igneous rock here, and this dark line represents our unconformity. So in the case of a nonconformity, what we're looking at is we're looking at rocks which were deep in the earth. They got pushed up, exposed, and they exposed for erosion. So erosion exposed these, so this became the surface of the earth. And then they dropped back down below sea level, and then they got covered in new layers of sediment. So in each of these three examples, the unconformity itself represents lost rock. And the only way we can lose that rock is by eroding it. So unconformities quite clearly show us that erosion has been happening in the past. The fourth type of unconformity is actually a little bit of a difficult one, is a paraconformity. So a paraconformity is, well, it looks like this. So here's our unit of rock above, here's our unit of rock below, and here's the unconformity itself. So we have horizontally bedded rocks above the unconformity, horizontally bedded rocks below the unconformity, and the unconformity itself is completely flat. So you can't see that it's there. The only way you know there's an unconformity here is if you can date this rock and this rock. So let's say this rock is 75 million years old, this rock is 70 million years old. That means this unconformity here represents 5 million years of lost rock. So the rock that was there was eroded away and it's gone. And so Hutton realised this, and this was a very strong piece of evidence to say that, obviously rocks have to be exposed and eroded, and then new sediment is deposited over the top. It was showing his system of uplift, erosion, deposition, lithification happening. And so when Hutton was the first to explain unconformities. So up until then, unconformities had been explained using what's called a Neptunist theory. So essentially, they said that the unconformity represented the land surface at the time of the Great Flood. So all the sedimentary rocks above the unconformity, they were deposited by the Great Flood, and anything below the unconformity was essentially pre-Great Flood. So what Hutton realised, as I was just discussing, was that he realised these unconformities actually represent periods of uplift and erosion before new sediments were deposited over the top. And his prime example of this is Sickaire Point in Scotland. So here's a picture of Sickaire Point, and you can see we have essentially a sequence of rocks. So here we have some red sandstones, and you can see they are dipping. Okay, so they have been tilted slightly, but they are near horizontal. Now below these red sandstones here, you can see we have another sequence of sedimentary rocks, but you can see these sedimentary rocks are near vertical. So we know that these sedimentary rocks here would initially have been deposited as horizontal sheets. So clearly what's happened is the sediment's been deposited, it's been lithified to form a rock, that rock has been tilted, so our horizontal sheets are now vertical. Now that tilting was probably due to uplift, so this sequence of rocks got pushed upwards, and during that process of uplift the rocks got tilted. So then they found themselves above sea level, and this surface here, the unconformity, represents the land surface. So any rock that was above this unconformity got eroded away. This was the surface of the Earth at the time. And then these red sandstones got deposited over the top. Okay, these red sandstones would have initially been nice horizontal layers of rock. They've been tilted a little bit since, but you can see what was going on. And so Siccar Point is a wonderful example of an angular unconformity. So if we just go back, here's an angular unconformity. Layers of rock below the unconformity are tilted. There we go, tilted. Layers of rock above the unconformity are horizontal. There we go. So this is a wonderful angular unconformity. The unconformity itself is coming through here like so. So once again, this is a wonderful example of Hutton's theory that rocks are essentially, sediments are created, deposited, lithified, so turned into rock. Then that rock has to be uplifted, at which point it's exposed. It can be eroded, producing new sediments, which then go to form new sedimentary rocks, and the cycle continues. Okay. So now let's have a think about numerical dating. So this is the process of taking a rock, or more accurately a mineral in a rock, and using radioactivity to produce a numerical value, an age that actually has a number associated with it. So the majority of the 92 naturally occurring elements in the periodic table are stable. However, a rare few of them are radioactive, and of course we've probably heard of them, uranium, thorium, radon, these are all examples of radioactive elements. So there's also a case that some elements which are normally stable, like potassium, will also have radioactive variants. So these are isotopes. So something like potassium 40, for instance, is radioactive. So if let's just nail down a few terms to begin with. So an element is defined by the number of protons in the nucleus. So 11 protons means your atom would be sodium. 79 protons would be gold. 92 protons would be uranium. That number never changes. The number of protons tells you what element it is. This is referred to as the proton number, and it's often given the notation Z. We also have the atomic mass. So the atomic mass is the combined number of protons and neutrons, which is abbreviated to N. So the atomic mass is always going to be larger than the proton number, with the exception of hydrogen. So an isotope is when elements can have variations in the number of neutrons in their nucleus, but the number of protons is the same. So for instance, we have potassium 39, potassium 40, potassium 41 and potassium 40. Okay, now 39 and 41, they're stable. Potassium 40, on the other hand, is radioactive. So we know as they're all potassium, they have to have the same number of protons. The thing that's varying to produce these different atomic masses is therefore the number of neutrons. So the number of neutrons will change, producing these different isotopes. So remember, we know they have to be the same element because the number of protons in each is the same. However, the atomic mass varies because the number of protons are different, and so, the number of neutrons are different. And so this gives us these different weights, and each of these different weights is classified as an isotope. So elements can have more than one stable isotope or more than one unstable isotope. So if we look at potassium again, we can see we've got potassium 39, potassium 40 and potassium 41. So potassium 39 and 41 make up the vast majority of all of the potassium out there, and less than 1% of potassium is the radioactive potassium 40. So typically when we write out elements, we obviously use the element symbol. So for potassium it's going to be K, and then we provide two numbers after it. The larger number is going to be the atomic mass, and that's located at the top. So remember, that's the number of protons plus neutrons. The lower number is going to be the proton number, so that's the number of protons by themselves. So we know in the case of potassium 40, we have a total of 40 protons plus neutrons. We know that 19 of them have to be protons, and so that means 21 would be neutrons. Okay, so we can work out pretty quickly, what the number of protons and neutrons are just by using our notation. So radioactive elements decay by emitting particles from the nucleus. They do this in an attempt to produce a stable nucleus configuration. So a radioactive isotope, by its very nature, is unstable. And the entire point of the radioactive decay is to try and take your unstable isotope and change it into a stable isotope, which will not decay. So it can do this by decaying in one of three ways. Now these are referred to as particle decays because the decay will produce a particle which will be thrown out of the nucleus during the decay, and that particle has mass. Okay, so as part of the radioactive decay process, it's producing a particle which it's getting rid of, and that particle is taking mass with it. So our three types of particle-based radioactive decay are alpha decay, beta decay, and electron capture. And these different types of decay are going to change the proton numbers and the atomic masses depending on what's happening. So in the case of alpha decay, your radioactive isotope is throwing out a particle that consists of 2 protons and 2 neutrons. So the particle it's getting rid of will take 2 protons from the nucleus, and those 2 protons will go with it. So that means that the proton number of your element is going to decrease by 2. Okay, so that's going to change what element it is. The atomic mass of your isotope is going to decrease by 4, because remember your nucleus just lost 2 protons and 2 neutrons. So alpha decay is going to decrease the proton number by 2 and the atomic mass by 4. So next we have beta decay. So in the case of beta decay, a neutron in the nucleus will spontaneously change into a proton. In the process, your proton, or your neutron should I say, as it changes into the proton, it will have to kick out an electron as a byproduct of that change. So this means that during beta decay, your proton number will increase by 1 because you've taken a neutron and you've changed it into a proton. The atomic mass, on the other hand, will not change. It will stay equal because, to all intents and purposes, a neutron weighs the same as a proton, and the electron that's being kicked out has negligible mass, so it hasn't really changed the weight of your isotope at all. So beta decay will result in an increase in proton number and no change in the atomic mass. The final type of radioactive decay is electron capture. In electron capture, we have a proton and it gets hit by an electron. So we have positive plus negative equals neutral. So we form a neutron. So as part of this process of taking a proton and turning it into a neutron, we end up kicking out this, which is a positron, which is essentially the exact opposite of an electron. Once again, though, the positron has mass. And so the positron getting kicked out is also a type of particle decay. So electron capture will cause the proton number to decrease by 1 because we've taken a proton and we've turned it into a neutron. However, as with beta decay, because all we've done is turn a proton into a neutron and they weigh pretty much the same, the atomic mass doesn't change. Now, there's another type of radioactive decay which I'm sure you've heard of, which is gamma decay. So gamma decay is the result of excess energy left over from particle decays. So a gamma decay does not produce a particle with mass. Instead, it produces an electromagnetic wave. So it's not considered to be a particle decay because at no point does anything with mass get kicked out of the decaying isotope. So this process of taking an isotope and turning it into a new isotope is called radioactive decay. So the isotope that's doing the decaying is referred to as the parent isotope, and it will decay over time to give us a stable daughter isotope. And so this diagram is summarizing what we were just talking about. In the case of alpha decay, the nucleus that's decaying will kick out a particle that consists of 2 protons and 2 neutrons. So that's an atomic mass of 4. And so that will cause our nucleus to decrease by the proton number of our nucleus to decrease by 2 and the atomic mass to decrease by 4. In the case of beta decay, we have a neutron turning into a proton, and that's going to kick out an electron as a byproduct. And so that means we've lost a neutron, but we've turned it into a proton. So remember, they weigh pretty much the same, so there's no change in mass. However, the proton number has obviously increased by 1. And then we have electron capture. So in the case of electron capture, we have a negative electron hit a positive proton. The two of them cancel each other out to produce a neutron. And so in this case, the proton numbers decreased by 1. But just like beta decay, the atomic mass hasn't changed because we've just changed a proton to a neutron and they weigh pretty much the same. So next question is well, what minerals do we want to use when dating a rock? Now remember, we can use the minerals to date the rock because the minerals are part of the rock. So that means when the mineral crystallized, well, that's part of the rock forming process, isn't it? So that crystal is considered to be part of the rock, and therefore we can use it to date the rock as a whole. So what we want is we want a mineral that will allow in the radioactive parent isotope into the crystal lattice, but not the daughter isotope. So if we are going to try and, let's say, date a mineral using uranium-238, that's going to be what we're going to use to date our mineral. Well, what we want is we want the mineral that we're going to use to date our rock. We want that mineral to let uranium into the crystal lattice of the mineral when it's forming, but not lead. So that means when our crystal first forms, it will have some uranium in it, but it will have no lead. Now that means, let's say, when we come along in, I don't know, 4.5 billion years, we will therefore know that any lead that we detect in that crystal is exclusively due to radioactive decay because there was no lead there in the first place. Okay, so that's very important. Our mineral has to let in the radioactive parent isotope, but it doesn't let in the daughter isotope. So that means when our crystal first forms, it has no daughter isotope in the crystal lattice. Okay, so if we're using a crystal of zircon, zircon will let uranium into the crystal lattice, but it will not let lead into the crystal lattice. So that means when we come along and we measure our crystal of zircon, any lead that we find must have come from radioactive decay. It's the only way it could get there. So yeah, the classic example is the crystal zircon. So zircon contains the element zirconium, and it just so happens that zirconium can substitute with uranium very, very easily. So as your zircon crystal grows, some of the zirconium will be replaced by uranium. So that means as your zircon crystal is forming, it will let in small amounts of uranium into the crystal lattice. However, lead cannot substitute for zirconium. It's the wrong valence and it's the wrong size. And so this means that when your crystal of zircon is growing, it will not let in lead. So when your crystal of zircon is all shiny and new, it means it will contain a small amount of uranium within it, but it will contain 0 lead. Okay, and that's very important. Because when we come along in however many million years and we analyze the crystal, well, all we've got to do then is we simply measure the amount of uranium, we measure the amount of lead, and then we add those two numbers together. And that gives us the amount of uranium we started with, doesn't it? Because think about it. Radioactive decay, all we've done is we've taken uranium and turned it into lead. That's all that's happened. So if we add the amount of uranium we have when we actually analyze the crystal, and we add the amount of lead we have when we analyze the crystal, add those two numbers together, that tells us how much uranium we actually started with. And so in that case, we now know the amount of uranium we started with. We know how much uranium is left in the zircon crystal when we analyze it. So all we have to do is just calculate how long it would take you to get from stage 1 to stage 2. That's all it is. And as you can, it's actually relatively basic math. It's not that complicated. So is there anything else we want when we're trying to find a good mineral for radiometric dating? Well, yeah, one of the most obvious ones is we would love it if the mineral we're looking at is common. the more common it is, the easier it's going to be to find, and the more of it there's going to be. And so that means you can analyze your rock more efficiently and more cheaply. If you have a situation where the mineral you're trying to date, is only an absolutely tiny proportion of the rock you're analyzing, well, then you're going to have to get, a huge sample of the rock. You're going to have to, process it, which is going to, take up time and money, and you're only going to get a few crystals to actually analyze at the end. On the other hand, if the mineral you're using is really, really common, well, then you don't need that much rock, and you're going to get loads of crystals which you can use for analysis once you've processed it, and it's going to be done faster and more cheaply. So a common mineral is helpful, and zircon is a great example of that, because zircon is a very common mineral. It's also helpful that your mineral is resistant to chemical alteration or weathering. So we want our crystal to be stable. So this means that over time, our crystal won't be damaged by chemical processes or physical processes. And so this means the crystal that we analyze in the lab will be the crystal that pretty much formed when it crystallized out from, let's say, the magma. Okay, it will be, nothing will have changed, because we want our crystal to be a closed system. The final thing we want is something which is called a high closure temperature. So a high closure temperature simply says, if I take my crystal of the mineral I'm analyzing, there's a magic temperature, and if you go above that magic temperature, your crystal can start to lose parent and daughter isotopes. Okay, so if you get the temperature high enough, the crystal lattice of your crystal will actually begin to weaken a little bit. And that will allow parent and daughter isotopes to actually leave the crystal. So you're losing material. You're losing parent and daughter isotopes. Remember, radiometric dating requires your crystal to be a closed system. It means you can't lose parent or daughter isotopes. But if you go above that closure temperature, well, then we start losing our parent and daughter isotopes. So then our crystal is no longer a closed system, and we can't really use it for dating our rocks. So what we want is a crystal that has a very, very high closure temperature, because the higher the closure temperature, the less likely it is that you will be able to reach that temperature. So the crystal will be highly unlikely to have lost parent or daughter isotopes. So half-lives range in length. They can be anywhere from billionths of a second. So hydrogen-7 has a half-life of about a billionth of a second, to 2 septillion years in the case of tellurium-120. Now, radioactive decay is not a uniform change. So what do I mean by uniform change? Well, think of you're putting a drop of water into a glass. So every time you put a drop of water into the glass, the level of water in the glass is going to rise up by the same amount each time, isn't it? You're not going to get that with half-lives. And I'm going to show you a graph in a second, which is going to show you what's going on. Now, the most important thing about half-lives and radioactive decay as a whole is that it's a constant. So the parent isotope is decaying to the daughter isotope at a set rate. So that means if we can take a crystal, so let's say a crystal of a mineral like zircon, and we can measure how much daughter isotope there is in that crystal of zircon, and we can calculate how much of the parent isotope the crystal started with, well, as long as we know how much of the parent isotope the crystal started with, and how much of the parent isotope is left when we measure the crystal, well, then we can very quickly work out exactly how long it would have taken to get from the starting concentration of the parent isotope to the concentration of the parent isotope that we can measure now. And the only reason we can do that is because radioactive decay is a constant. It's like a second hand on a clock. It's constantly occurring at a set rate. So okay, so we have a couple of different ways of looking at half-life. So let's look at the table over here to start with. So this table has 4 columns. So the half-life, so that's the amount of the parent isotope remaining. So here in the percent, this is how much parent isotope remains in the sample after every half-life. So as you can see, at half-life 1, our sample contains 100%, sorry, half-life 0, sorry, our sample contains 100% parent isotope. So we're starting off with 1 million isotopes of the parent isotope, and obviously because no decay has happened yet, we have 0 daughter isotopes. After one half-life, 50% of the parent isotope has changed from the parent to the daughter completely. After two half-lives, well, that's half of this number has now turned into the daughter isotope. So now, as you can see, the parent isotope has decreased by half from the previous amount, whereas the number of the daughter isotopes has now increased by 250,000. So what you're going to notice is the amount of parent isotope each time is going to decrease by half, and obviously the remainder is going to be added to the daughter isotope column. The most important thing to think about is that we're not actually losing anything. So if you take a second and you start adding up all these numbers, what you're going to notice is you always end up with 1 million isotopes. Because all we're doing is we're taking parent isotopes and turning them into daughter isotopes. We're not actually losing anything. So the numbers of parent and daughter isotopes never change. It's just simply the ratio between them will change over time. So every half-life we lose essentially half of the previous amount of the radioactive parent isotope. So if we look at this graph over here, we have the same situation. So here's our mineral, and in our mineral we have 100 isotopes of our radioactive parent. Okay, obviously because no decay has taken place yet, we have 0 daughter isotopes. After one half-life, we go from here to here. So this is essentially 50% of the parent isotope turned into the daughter isotope. So now we have 50 atoms of the parent isotope and 50 atoms of the daughter isotope. From half-life 1 to half-life 2, the amount of the parent isotope halves again. So by half-life 2, we have 25 atoms of the parent isotope and 75 atoms of the daughter isotope. From half-life 2 to half-life 3, the amount of parent isotope halves again. So now we have 13 atoms of the parent isotope and 87 atoms of the daughter isotope. From half-life 3 to half-life 4, the amount of parent isotope halves again. So we now have 6 atoms of the parent isotope and 94 atoms of the daughter isotope. So every time we go from one half-life to another, the amount of the parent isotope is divided by 2. Now, the most important thing to remember is the amount of time it takes you to get from half-life 0 to half-life 1, and from half-life 1 to half-life 2 is the same. So let's just say, for argument's sake, it takes, the half-life is 100 million years. So it's going to take you 100 million years to get from here to here. It's also going to take you 100 million years to get from half-life 1 to half-life 2. It's going to take 100 million years to get from half-life 2 to half-life 3, and it's going to take another 100 million years to get from half-life 3 to half-life 4. Because radioactive decay is a constant. The rate doesn't change. It doesn't matter how many isotopes of the parents you have, the rate of decay is still always going to be the same. So once again, as long as we know the amount of the parent isotope we start with in our mineral, and we know the amount of parent isotope we have left over when we actually measure the crystal, well, all we have to do is we just have to work out exactly how long it will have taken, the amount of parent, it will have taken, how long will it take for the parent isotope to break down to give us, the amount of parent isotope that we have now. That was an absolutely horrendous explanation, wasn't it? And I do apologize. But the most important thing is as long as we know how much parent isotope we start with, and how much parent isotope we have left when we actually measure the crystal, we can work out very, very easily how long it will take us to get from the amount that we start with to the amount that we see when we actually analyze the crystal. And we can do that because the radioactive decay is a constant. So if we look at half-lives, you'll notice very, very quickly that half-lives are not the same. So depending on what's actually decaying, the half-life will vary. So here we have 5 of the most common half-lives used in geology when it comes to dating rocks. So we have uranium-238, uranium-235, thorium-232, rubidium-87 and potassium-40. So you'll notice that for uranium-238, the half-life is about 4.5 billion years. So that means that about over half of the original uranium-238 that was in the Earth when it first formed has now decayed to lead-206, because of course the Earth is 4.56 billion years old. In the case of uranium-235, the half-life is 700 million years. In the case of thorium-232, the half-life is 14 billion years. So, you know, the universe is very quickly moving to being 14 billion years old. So, you know, we're pretty close to, you know, all the thorium in the universe, or the thorium-232 in the universe achieving its first half-life. So rubidium-87 has a half-life of nearly 49 billion years. That's a pretty big one. And potassium-40 has a half-life of around 1.3 billion years, quite, you know, another long half-life. But the most important thing is the half-life doesn't change. It doesn't matter how many parent isotopes you have, the half-life is a constant.